Problem statement number one. A bank receives an average of 5 customers per hour. Okay, let's say that's given to you that the bank receives 5 customers every hour. What is the chance that exactly 3 customers will arrive in the next 1 hour? Problem number two. Scientists have observed that on an average, 2 meteorites they strike the Earth every single year. That's the average. What is the probability? What is the chance that 3 or more meteorites are going to strike the Earth in a given year? These types of questions are answered using Poisson distribution. This session is all about Poisson distribution. So Poisson distribution, it's a discrete probability distribution function. It gives you the probability of a certain number of events happening. Okay, events happening in a fixed interval of time, distance, area, or volume. Now we make an assumption. We make an assumption, and the assumption is that your events they always occur independent of each other, and they occur at a constant average rate, denoted by lambda. Now, the probability of getting exactly k events in a fixed interval is given by this formula right here. Okay, this is how your Poisson distribution is expressed. Your lambda is the average number of events, your mean rate. Your k is the number of occurrences, meaning how many times it occurred. E is your Euler number. So it deals with the type of situation where you have to determine k. For example, let's say you want to determine the number of customers arriving at a bank in the next 45 minutes, or maybe number of phone calls received at a call center in the next 2 hours, or number of patients arriving at a hospital in 2 minutes, or number of typing errors per page, number of car accidents in a given day, or number of data packets arriving at a server per second. Let's say you have a bank. It receives an average of 5 customers every hour. Assume that these customers they arrive at the bank independent of each other. Okay, and the average is constant, meaning the average of 5 customers per hour that is constant. So, what is the probability that exactly 1 customer will arrive in the next 1 hour? What is the probability that exactly 2 customers will arrive in the next hour, and 3 customers will arrive in the next hour, or 4 customers arrive in the next hour? So, you have these 4 questions. Let's deal with them. So here my lambda is given to me. That's basically your average number of customers per hour is 5. That's given to us. K is the number of occurrences. In other words, the number of customers arriving in the next 1 hour. So applying this formula, I'll be using this formula right here. Okay. So substitute your value. I know my lambda. My lambda equal to 5, right? So I'm substituting my 5 right there. This is my 5, and my in this case my k. I want to know the probability that exactly 1 customer arrives. So in this case, my k equal to 1, right? So substitute my k equal to 1 in this expression, and the answer comes to be 3.37. So the probability that exactly 1 customer will arrive in the next 1 hour is 3.37%. How about 2 customers? Well, use the same formula. Substitute your value of lambda, which is 5, same value. Substitute your value of k. In this case, it becomes 2 because it's a 2 customers. And put the 2 at the bottom, 2 factorial, and the answer comes out to be 8.42%. So the probability that exactly 2 customers will arrive in the next 1 hour is 8.42%. Likewise, for 3 customers, you substitute your formulas in there. This is e to the power minus 5 plus 5 to the power 3, and your answer comes out to be 14.03%. And for 4 customers arriving, the answer is 17.54%. Now, I'm plotting this over here. So the first one that I did was x equal to 1, right? This one right here. So the probability that exactly 1 customer arrives is 3.3%, which is right here. Okay, this is my first one. The next one is probability that 2 customers arrive, that exactly 2 customers arrive is 8.42%. So which is this right here. So 8.42 is somewhere, let's say over here. Okay, so this is my 8.42. The next one is 14.03. So the probability that exactly 3 customers arrive, which is right here, is approximately 14 point something. So this is the third, and likewise exactly 4 customers arrive is somewhere over here. The answer is 17.54. So this is how I'm plotting these stem plots over here. So you can see the trend. It's kind of like going up like this. Okay. Now, let's take a look at this thing. So let's say if I increase the value of k. Okay. So just to experiment, I'm increasing the value of my k, and you can see that how your Poisson curve looks like. You can see your Poisson curve actually goes up and up. Okay, you can see it's going up, 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 up right here, and then it starts tapering off, then it starts going down like that. So this is the number of events. In this case, this is the number of customers arriving in the next 1 hour, and you can see the shape of this curve. It's almost like a bell-shaped curve, not exactly a bell-shaped curve, but it's kind of like following that curve. Now here I'm actually increasing my lambda, and as you can see that here my lambda equal to 1. Okay, this is my lambda equal to 1. Here my lambda equal to 2, and here my lambda equal to 3. Okay, and here my lambda equal to 4. You can see that as your lambda is increasing, your curve, okay, you can see that your curve is almost taking a shape of a bell curve. So this is one of the characteristics of your Poisson distribution. So scientists, they have observed that on an average, two meteorites large enough to be detected by your ground-based sensors, they strike the Earth in a single year. Okay, that's what they have observed. Assume that your meteorite, they strike randomly and they are independent of each other. Each strike is independent of each other. And they're happening at a constant average rate. Let's say it is lambda equal to 2 per year. Okay, this is two meteorites striking every single year. That's the average rate that they have noticed. Now find the probability that two or less meteorites are going to strike the Earth in a year. Find the probability that three or more meteorites are going to strike the Earth in a year. So let's do question number one first. The probability that your two or less meteorites strike the Earth in a year is given by this expression. Probability of x is less than or equal to 2. In this case, my x is the number of, it's a random variable that indicates the number of meteorites striking the Earth. So in this case, the probability of x less than or equal to is given by probability of x equal to 0 plus probability of x equal to 1 plus probability of x equal to 2. Because you can have 0 meteorites striking, you can have one meteorite striking, or you can have two meteorites striking. So you just add them all together. So let's calculate our probability of x equal to 0. Substituting into this formula, this is my formula right here. Okay, so in this case, this is going to become e to the power minus lambda. Now your lambda in this case is 2 times your lambda to the power k. Your k in this case is 0 divided by 0 factorial. Okay, so this is my first expression right here, plus. Okay, then I'm going to this expression. So this is my right here, is my first expression. My second expression is going to be e to the power minus 2, all right, times lambda. In this case, lambda is 2 to the power 1 divided by 1 factorial. All right, so this is going to be my second expression, which is this one right here. And my third expression is going to be e to the power minus 2 times, in this case, 2 to the power 2, right, divided by 2 factorial. And that's my this expression right here. So you calculate all these values, all right, and my answer comes out to be right here. These are my corresponding values over here. Then you add them all together and your answer is 67.67%. So 67.67% chance that you're going to have two or less meteorites tracking in a year. So if you plot this on a little stem plot right here, if I do a little stem plot, so this is my 0 right here. So probability of 0 meteorites tracking is 0.13 approximately. So this height is 0.13, and this one right here, probability of striking one meteorite is 0.27, and probability of striking two meteorites would be 0.27. So I just do a little stem plot over here. Now, the probability that three or more meteorites strike the Earth in a year is given by this expression, the probability that x is greater than or equal to 3. Well, this is same as saying the probability of 1 minus p x is less than or equal to 2. Now, the reason I'm working with this is because I already have done calculation of this previously. So since I've already done this calculation, I can just substitute the values over here. It's going to become 1 minus 0.6767, and the answer comes out to be 32.33%. So it's 32.33% chance that you are going to have three or more meteorites striking the Earth in a given year. So by the way, just on a side note, this Poisson distribution, they're often used in astronomy, space science, okay, for modeling your meteorite impacts, for your supernova occurrences, for your gamma ray burst, your cosmic ray detections, because these are very rare and random, and these are independent events over space and time. So this is one of the application of that. So by the way, so I plotted this thing for 0, okay, my k equal to 0, k equal to 1, k equal to 2, and you can see the shape. You see the shape is going something like that right there, okay. And so this is how your shape looks like for your Poisson distribution in this particular, for this particular lambda equal to 2.